Welcome back to AP Calculus AB, Topic 2, Derivative Rules and Tangent Lines. Hopefully by now you've noticed we do tangent lines pretty much every day. And in order to get to those tangent lines, we use different rules for derivatives. We started this whole unit with limits. We've gotten a few derivative rules now, namely the power rule. That was a big one. And then just last class you learned the product rule. And so it should only make sense that today we're going to cover the quotient rule. So let's begin. We know that we can rewrite division as multiplication using negative exponents. Well, looking at this, if we saw d dx of e to the x divided by x, one thing we know for sure is that we are not allowed to just say, oh, we're going to take the derivative of e to the x, and we're going to take the derivative of x. So this would stay itself, e to the x, easiest derivative we know. This would become 1, and the answer is e to the x. That is not it. We need to realize that we are not allowed, when we have division or multiplication of two functions of x, we are not allowed to take the derivative of each individual part. We can only do that with addition and subtraction. So that's a big no-no. So what do we know? Well, we actually know a different way to take care of this. We can say, instead of the derivative of e to the x divided by x, let's rewrite this as e to the x times x to the negative first. And this is what we covered last class. We learned, and this is a nice reminder up above, that if we have, or we are asked to take the derivative of two functions multiplying, we do the derivative of the first one first and keep the second one the same, and then we keep the first one the same and multiply it by the derivative of the second. Let's make sure we remember that what that looks like down here. Derivative of e to the x is just itself. We keep the second one the same. And then we add on the original first function, which is e to the x, and multiply by the derivative of the second, negative 1x to the negative second. And there we have it. Now, we should probably clean this up a little bit. Those negative exponents usually don't show up in our answers, so we'd rewrite it, right? We'd bring it down. And then this one up, there's a negative 1 in here, so let's bring that negative out front, e to the x positive. And then we bring our exponent down. And we could, of course, keep going. It's always good practice to simplify algebra just to keep you comfortable with it in case that shows up on a multiple choice exam. We should probably give these two common denominators, right? This was missing an x to make it x squared, so we have x e to the x over the common denominator x squared minus e to the x divided by x squared. Putting this all together, we end up with x e to the x minus e to the x over that common denominator, and maybe even going a step further, e to the x is common to both, so we can factor that out. And that's probably as simple as we can get. Okay. Now, just as a reminder, you're not asked to simplify on free response questions, so if you wanted to stop here, that's allowed, right? That is an answer. There's equal signs between this and everything else down here. All of these are equivalent. There's no rule of when you have to stop. So my suggestion on a free response question is stop as early as possible, right? Stop right here. If you continue to simplify, and let's say that you miss like a negative sign, let's say you made this a plus at the end, you actually lose the entire point for the answer there. Usually an answer is only 1 point, right? So this is worth the 1 point, and it's worth the same 1 point as this down here. But if you write something incorrectly, then you lose the entire answer point. So stop when you're right. Quit while you're ahead. Now, what we're going to try and do is see if we can generalize the result of one function being divided by another, right? That's our quotient when you divide two quantities, without using negative exponents. And the reason we're not going to use negative exponents, the reason that this technique up here doesn't always work, is when we get to more complex functions than just x to the n. For example, if we had like 3x minus 2 to the n, the derivative, of 3x minus 2 to the n is actually a little bit trickier than just x to the n. So we want to try to be able to do this without using negative exponents, especially when our functions become harder. So what we're going to do is define h of x as the function for which we want to try to find the derivative, right? Our end goal here is we want to try to find an answer for h prime of x, just h prime of x equals. And h prime of x is currently defined as functions f and g. So we want to make sure that our answer over here, whatever this ends up being, whatever our formula is for the derivative, only has functions f and g in it. It's kind of like when we did the product rule up here, we got the derivative of f and g and our answer only had manipulations of f and g. It had some primes in there, but that's still all based off of things that were given to us. Now, how do we do this? Well, the first thing we're going to do is get rid of our denominator. So we should probably go ahead and multiply by g of x on both sides. That gets rid of the issue of having to deal with this fraction, which is the quotient. We don't have a quotient rule yet. So I think that's going to give us g of x times h of x is equal to f of x. And that's useful because we know how to take the derivative of each side. So technically in between here, and you don't need to write this step, I'll just show it just in case, we're multiplying g and h together and we want to take their derivative, and of course whatever we do to one side, we want to do that to the other. Now why am I taking the derivative of each side? Well, remember our end goal. We want to find h prime of x equals something, so we need an h prime of x, and my problem doesn't have h prime until we go and take the derivative. Okay, product rule for the left side, g prime of x, keep the second one the same. Now we keep the first one the same and multiply by the derivative of the second. Of course, the derivative of f of x is just f prime. Again, we have not met our goal because our goal we want to isolate, or we want to have an equation for h prime of x, but luckily our algebra skills are solid, so let's go ahead and try to isolate h prime of x. I would say first step is we'll probably need to subtract off the g prime of x and h of x to the other side. Right? That's going to become f prime of x minus g prime of x, h of x. And we're doing that because, again, we're trying to isolate this guy. But in order to isolate, I think we'll probably want to divide by g of x on both sides now. And that gives me something that's looking pretty good. We have h prime of x equals f prime of x minus g prime times h of x, all divided by g of x. And actually, this is a version of the quotient rule. However, nobody's going to write the quotient rule like this because the quotient rule is calling itself in its rule. It's saying to find the derivative of h prime, we're going to move h over to the right side, and that's just generally not done. I mentioned up above that when we take the derivative, we want to make sure that the right side over here only has combinations or manipulations of the functions f and g. Well, can we do that? Well, I think we actually can because we know what h of x is equal to. H of x was defined as f of x divided by g of x. So let's rewrite this and then simplify a bit. H prime of x is going to be f prime of x minus g prime, and our nice little substitution, instead of h of x, we know that is f of x divided by g of x. And then this is all being divided still by g of x. And there's nothing wrong with this. It is, again, no problem, perfectly correct, except it's weird to have a fraction within a fraction, that complex fraction issue. So what I'm going to do instead is go ahead and multiply the top and bottom by this denominator so that we can undo it. So we'll multiply the top and bottom of our fraction, numerator and denominator, by g of x. And we're going to have to be okay with our distributive property, but it's good practice for us. We'll distribute g of x over here, and I think that's going to give me f prime of x times g of x. Note the similarity to the product rule, derivative of the first, keep the second the same. Now there's a minus though. Product rule has a plus, product plus. And then I need to take g of x and distribute to this entire term, right? This is all one term here, so it's not going to be g of x times this and that. No, it's just the whole term. And when we do that, since we have a division of g of x and a multiplication, those cancel, and leaves me with g prime of x times f of x. All divided by, when we multiply something times itself, it is that thing squared. And now we have a quotient rule. And you might be like, whoa, that rule seems awful. How am I ever going to memorize it? Well, it is something that you do have to memorize. We use the product rule and quotient rule a lot, and there are some situations where you just have to use the quotient rule. Or it's just going to be way faster than switching it around using negative exponents to use the product rule. So here's how I like to remember it, and I'm going to write the product rule right on top of it. So our product rule was f of x times g of x. And look at the similarity. Derivative of the first, keep the second the same, plus product rule has a plus. First one times the derivative of the second. Look how similar those two are. They're pretty much the same. The only difference, of course, the reason why they're not the same is that both the negative and the quotient rule, and it's called the quotient rule, so there's probably going to be a quotient in the rule as well. And there is. We are dividing by the original denominator squared. Okay. And that shouldn't surprise you too much either, right? If you had f of x divided by x and you wanted to take the derivative of that and you didn't know the quotient rule, you'd do what we did before and you'd bring that x up to the top, right? So when you end up doing the derivative, and it's going to come in the product rule later on, but the derivative becomes negative 1x to the negative second. It increases the exponent by 1. So if this is x to the first, it shouldn't shock you that this is x squared, right? Because it's x to the negative first becomes x to the negative second. Regardless, though, you do need to memorize both the formulas that are on your screen. You will use them almost certainly daily for the rest of this semester, at least one product and one quotient. Make sure you commit that to memory. Of course, the easiest way to commit it to memory, practice it. Practice improves performance. We want to improve our performance as best as possible. A few examples, of course. d dx of x divided by e to the x. I'm going to go ahead and rewrite my quotient rule maybe directly underneath, and we can just work bottom to top, which is strange, but that's fine. So f divided by g. Derivative of the first, keep the second the same, keep the first the same, derivative of the second, divided by the bottom squared. Okay. And so when we're looking over here, maybe we have our, I should have done this in colors, but that's okay. Maybe we have our top function right here, I'll do in red. So derivative of the first, easy enough. I always put parentheses, it's up to you. And then the bottom function I'll keep in gold, times the derivative of, or times the bottom one stayed the same, minus, now we do the derivative of, or keep the top one the same, I'm doing great here, and we do the derivative of the bottom, which is e to the x, all divided by the denominator squared. That's it. Now, could we clean this up? Well, of course we could. You might notice that in the top we have e to the x, which is, ooh, you cannot see that at all. We have e to the x, which is in common to both of them, so why don't we factor out an e to the x? That leaves me with the 1 and the minus x that were attached to each of those as coefficients, and we get, well, e to the x squared, just as a heads up, because this comes up a bunch, especially on, maybe a knowledge check from next class, but e to the x squared, of course, means write e to the x times itself. And then you have a couple things to do here. Well, first, you could realize that you could just cancel, and that's probably the best thing to do, because why not? I mean, it's a good way to go. But the other thing that we could do here is you could write e to the x times itself. Same base means you add the exponents, so that's actually e to the 2x. So e to the x squared is not the same as e to the x squared, it's e to the 2x. However, I would probably just cancel both of those and end up with the answer 1 minus x divided by e to the x. Okay. So nothing too terrible. It is, I think, almost the same as the opener, right? You'll notice that the opener flipped this over, so it stayed a little bit different, not quite the same, but that's okay. So here we go. Let's look at a couple more. Example 2. Please find the derivative in 3 different ways. We are going to compare and contrast those 3 different ways, but why don't you pause this video, see what you can do, and then once you're done seeing if you can find it in 3 different ways, hint, power rule, product rule, quotient rule, go ahead and unpause and we'll go through it. So hopefully you took the time to go through this. We'll go most complicated to least complicated, I think. So the most complicated in this case is going to be my quotient rule, which I often abbreviate as QR. So our quotient rule is going to have us do the derivative of the top function first. The derivative of 6 is 0, and we keep the bottom function the same. Notice when I write the bottom function, it's x to the ninth. I'm not bringing this up. It's not x to the negative ninth. That's a really common mistake we see students make. They think, oh, this is in the denominator, so when we write it in the numerator for the quotient rule, it becomes x to the negative ninth. No, the quotient rule is cool because it just takes these two functions as separate entities. It doesn't matter whether it's in the numerator or denominator of the fraction. Okay, quotient rule minus, keep the first one the same, derivative of the second, 9x to the 8th, all divided by the denominator squared. Cleaning this up, well, 0 times anything is 0, so no need to do that. I think we'll have to do 6 times 9, that's 54 with a negative x to the 8th, and then with these two, again, x to the 9th times itself, add the exponents gives us x to the 18th, it's not x to the 81st. And I think we can probably simplify a bit here. We have 8 x's on top and 18 on the bottom. If you imagined writing out all those x's, doing the same thing down here, you'd cross off a bunch of them. In fact, you'd cross off all 8 of the ones in the numerator, and that would leave you with 10 in the denominator. So negative 54 divided by x to the 10th. That's our long one. All right, what's the second way? Well, the second way is, of course, using the product rule. I tend to use PR for product rule. Power rule, we're really going to stop talking about pretty soon because it's going to become such second nature that you're just not going to screw it up. So quotient rule, product rule, QR, PR, very common coding on our knowledge checks and on our tests. If you forget to use one, I will use that coding, so be ready for it. How do we use the product rule in this case? Well, we're going to have to rewrite this quickly as 6 times x to the negative ninth. So when we bring that up, if we haven't done a derivative, we do need that negative exponent. Okay, product rule. Derivative of the first, keep the second the same, and then add on plus in the product rule, keep the first the same, derivative of the second looks something like, oops, getting ahead of myself, looks something like this, I think. Well, one bit to clean up becomes 0. The other one, 6 times negative 9 is negative 54, and bring the x to the 10th to the denominator. Right, there's way 2. However, I said we'd go most complicated to least, and I meant it. Let's look at just our traditional power rule. But we can only use the power rule if it's rewritten in our format of 6 times x to the negative ninth. 6 is a constant, so I'm going to ignore that, and you probably wouldn't show this step, but that's okay. And then we just use our power rule. So it becomes negative 9x to the negative 10th. And we can see that's negative 54x to the 10th. Full disclosure, I probably would have done this problem just going from here to here, or maybe from here to here. That middle step is definitely a little bit extra, but there's nothing wrong with showing more work. Regardless, we get the same answer in all 3 ways. You're never going to be required to use a specific method if there are other methods available. However, there are definitely cases where this method won't work and maybe this one doesn't work, but this one does. So you need to know all of them and be able to apply it to specific situations. This next part is designed for partners, but this is the year of COVID, so you're not actually allowed to switch papers. So you're really going to be working on your own. You can hold up your paper and share with your partner if you want, but let's make sure we understand the rules. They are asking you to do the problem twice. The first time they want you to do it using the quotient rule, and the second one, if possible, they want you to do by rewriting the fraction. So let's get started. Problem 1, go ahead, and if there's someone nearby, you should try this one. Your partner should try this one. And then once you've each done that, you need to make sure your answers match. On the second part, you guys are going to switch. And now your partner is going to tackle the first one and you're going to tackle the second one. You don't need to go back and do both sides. If you'd like, of course, for the extra practice, it's never a bad thing. You can. So go ahead and pause my wonderful voice for now. Try problem 1 and problem 2, and then unpause when you're done if you want to see how I worked through it. Okay, I'm going to tackle the quotient rule in this column and not the quotient rule in this column. Quotient rule wise, well, we should probably realize that 3x squared has nothing to do with the quotient rule, so I'll keep that one separate. But the second one, we can use the quotient rule. I would almost certainly not use the quotient rule here. Whenever there's a constant in the numerator, the quotient rule just gets tedious. But this is our practice. So 3x squared, nothing too terrible. That just becomes 6x. The second one, here comes our quotient rule. Derivative of the first, keep the second the same, keep the first the same, derivative of the second, 7x to the 6th. No negative exponents here. Quotient rule keeps it as written. And this is x to the 7th, of course, squared. Now, you can stop here, and I am going to stop here, because why do more work if we don't have to? Let's go ahead and try the not the quotient rule. When we do our not the quotient rule, I'm again going to split this, ddx of 3x squared, and also ddx, we are going to rewrite it this time, 6x to the negative 7th. This becomes 6x. The second piece, well, I'm going to switch the plus to a minus. I can see that negative coming in, right, rearing its ugly head. So minus 42, 7 times 6, x to the negative 8th. And you can stop there. But the problem is, well, this is the same problem, and you should be able to match your answers. So you can work through one way or another, whatever sounds good, but I'm going to work with both of them. I'll tackle this one first, and I'm going to rewrite this as 42 divided by x to the 8th. And I think that seems okay. That's actually looking pretty similar to this over here, right? They kept the 6x separate. Why not? So if we work with this one, can we match that? Well, this becomes 0. Oh, there's that negative again, so maybe I'll just write it like this. Minus 42x to the 6th divided by x to the 14th. Yeah, 7 times 2. And then reducing like we did in the previous problem. Let's move that negative out front now. We have 6 x's on the top. You're going to be able to cross off all 6 of them. And if you take 6 out of the 14, it's going to give you an 8. So I think that gives you minus 42x to the 8th. Our answers match, and we are good to go. The second one is a similar idea, but things are getting a little more complicated here. So let's attack this quotient rule first. Quotient rule, we have to do the derivative of the top first, derivative of the first one first. So this is going to be 3x squared plus 6x plus 1. The derivative of x, the slope of the function x is 1. Keep the second the same. Minus, now we keep our first the same. 3x squared plus x, and we do the derivative of the denominator, which is 3x squared, all divided by the denominator squared. And again, I'm going to stop there. That is the right derivative. If it's a free response, don't go further. Stop. You're golden. You're glorious. Why would you do more work if you don't have to? However, let's go ahead and check our other problem. How are we going to do this? Well, I think, and we discussed this before, you could either bring x to the third up and distribute, or for whatever reason, my personal preference is to make 3 fractions here all over that x cubed common denominator. I'm not sure if this is actually faster than the other way, but I've always been partial to it, so that's what I'm rolling with. 1 plus, we can cross off 2 of our x's, that just leaves me with a 1, so 3 over x, and why don't I write that as 3x to the negative first so I can avoid the quotient rule, and then take away 1 of the x's, that leaves me with 2 of them, so 1 over x squared, or x to the negative second, and let's take the derivative of each piece. The derivative of 1 is 0. Next part, the negative 1 is going to come down, negative 3x to the negative second, and our last one becomes minus 2x to the negative third. Ha! This does not look like my answer at all, and that is a bummer. I'm actually going to do a little work with the yellow one because I can do a few steps and then I can go work with the more complicated one. With the yellow, I'm at least going to go ahead and write them over common denominators. Clearly their denominators are not common right now. I think this one is missing an x to be common. And I think this is going to give me negative 3x minus 2 in the numerator divided by x cubed. So this is looking a little bit better. I think we still have some cleanup to do. Well, how am I going to clean this guy up? Well, I can see a couple things that might make our life at least a little easier. In particular, this has something in common to each term. I see an x squared. I know there's an x cubed here, but it at least has an x squared inside. So I think maybe the first thing I'll do is factor out an x squared from everything. Let's see what this does. We may have to do some extra cleanup after. So 3x squared plus 6x plus 1, and then x cubed, I took an x squared out, so now there's only an x left, minus, and then there's a 3 here, might as well move that to the front, and then we have x cubed plus 3x squared plus x. Good, all divided by, and then I'll write this as x cubed times x cubed, right? Or honestly, just to save ourselves some time, this is x to the 6th. X to the 6th is just 6x is multiplying, I think, right? Something like that. And that'll come in handy, right now. Because we have x squared here, that's x times x. That's going to get rid of 2 of the x's multiplying here. Don't make the mistake that you think we can get rid of this x. We can't, right? Because there's subtraction in the middle. We could only cancel out that problem at the beginning because it's a factor multiplying by one other whole factor. So I think when we clean this up, we'll probably need to distribute our x's in here, and maybe let's distribute the -3 over here and see what happens. In fact, we could have been really clever. You could have noticed that this has an x as well, so you could have factored it out to make an x cubed and pull it out, but that's fine. We can take care of it later. So we have 3x cubed plus 6x squared plus x, and then distributing the negative, minus 3x cubed minus 9x squared minus 3x, all divided by x to the 4th. Any like terms here? Well, the 3x cubes cancel, which is good because I don't see an x cubed over here. And then we have some like terms to combine. We're almost done here. 6 minus 9 is going to give us negative, math is hard apparently, -3 of those x squareds, and x minus 3x's will give us -2x. Look how close that looks. We're getting there. Divided by x to the 4th. What's still in common to the numerator? Well, an x, of course, and we have -3x minus 2 divided by x to the 4th, and hopefully we can see these cancel, leaves us with the 3, and we have matched our answer. Again, could you have stopped at the beginning? Sure, but sometimes those multiple choice questions do you not a solid and have you reduce, and so you need to be comfortable reducing. Additionally, when you do the quotient rule in the textbook, they do some of the craziest reductions, and what I've done in my worked out solutions for your independent practice is I've showed you how to get to the answers that are in the back of the book. Again, I am definitely of the mind, stop early. But should you try to match the answers in the back? Yes, you should, because you need to practice your algebra skills. All right, this is our last part of today, and we get to do some FRQ practice here. This was a free response question from maybe 2 or 3 years ago. I'm estimating this was either 2017 or 2018 on the BC exam, probably 2018 actually. And this problem actually made me realize that I was not the world's best teacher, which I'd actually never thought that, and I still don't, but it actually made me realize that I'd somewhat failed my students. I felt bad, and I'll bring that up again near the last question. However, what you should do again is pause. You should read the stem of the question, realizing it applies to all parts A, B, and C, and then you should try parts A, B, and C. Technically, there is a 4th part here. I think this question at the end is technically D, and we're missing part C or something. The reason that we're missing one of the parts is because you don't know how to do it yet. The way the free responses work on the AP exam is they're usually between 3 and 4 parts, and they're cumulative throughout the year. They're not focused on a certain theme. It's not going to be like, here's a free response on derivative rules. No. Derivative rules are scattered throughout the free responses. Limits are scattered throughout. And so that means that generally each free response tests you on material from the entire year. So as we get some free response questions, I've retyped them, and then I take out the parts that you don't know how to do yet. So this is an open free response question. By open, I mean that it's non-secured, which means the answers are purposely posted on College Board's website. So if you ever want to spend some time when you're preparing for your AP exam, pull up the College Board website, or you can pull up my AP, and do some free response problems. When I first got my job as an AP Calc teacher, and this was 7 or 8 years ago now, I literally did every released free response question, every single one. And let me tell you, there are lots. It took me like a month, not a joke. And really, until you can do all of them pretty comfortably, pretty quickly, you're not going to have that fluency that the AP exam wants you to have. Now, do you have to do them all? No. But if you have the time before the AP exam, maybe over spring break or so when we're done with our material, should you start working through them? Yeah, we'll do tons of them throughout the year, but it's never a bad thing to see it more than once. So, my long tirade about FRQ practice is done. Pause me, try these problems, and then we'll do them together. Okay, what did this problem give us? Well, they give us 3 functions here, and they're telling us a couple things about those 3 functions. In particular, right, we know that g of 2 is 4. Maybe I should list all of these as well. So we know that g of 2 is 4. I'll try to keep my colors consistent. We know h of 2 is also 4, right? That's what they tell us here. And then they also have a line tangent to both the graph of g and h. So we need to remember a couple things about tangent lines too. I think that's going to make this go a lot faster. This line here is tangent, right? Maybe I'll call it t of x in case you wanted to use my notation for it. If it's tangent, we should be able to get a few things out of it. First, what form is this in? Well, 4 plus 2/3 x minus 2. Notice if you move that positive 4 to the end, it becomes plus 4 here. This is just our HK form, isn't it? And our HK form has this very generic form, and I'll do it once with g and once with h. If I was talking about the tangent line to function g, then we would write this as, and we know it's happening at 2, don't we, right? So it's x minus 2. Well, then this output is g of 2, and this beginning piece is g prime of 2. And then if we thought about it, because it's also the tangent line of h, then we could use the same format, h prime of 2, x minus 2 plus h of 2. So this tangent line is both reaffirming what we already know in that the point 2, 4 is common to both of these, but it's also giving us an additional piece of information. It's giving us the slope for each of these graphs at an x of 2. And how do we write that? Well, we write it as g prime of 2, based on our tangent line, has to be 2/3. And h prime of 2 has to also be 2/3. Let's begin. A, find h prime of 2. Wait, is this a trick question? We know h prime of 2. Well, it's not a trick question because what they're testing here is, do you understand what makes up a tangent line and what happens when a tangent line is tangent to a graph? So they're testing to make sure you understand that this is the slope not only of the tangent line, but also of g and also of h, all at 2. So in fact, they didn't even ask for any work here. All you need to put here is h prime of 2 equals 2/3. If it makes you feel happy, you can write a sentence. You can say, we knew this because the tangent line has a slope of 2/3, and in order for 2 functions to be tangent, then they have to have the same slope at that point, something like that. However, that's all we need here. Woohoo! Moving on. B. Let a be the function given by a of x equals 3 times h of x divided by x squared. Write an expression for a prime and then find a prime of 2. Okay, a prime of x first. That seems like a thing that we should do. I'll use, what did I do, h in yellow? Sure. So, a prime of x. Well, how do we do the derivative of this? I see one function being divided by another, which to me means that we probably need the quotient rule. Okay. So, quotient rule wise, derivative of the top. Well, 3 is a constant, so when I do the derivative of the top, the constant just hangs out. It's like, cool guys, I'm going to watch the derivative happen, next to me. So, derivative of h is just h prime of x, right? We don't have a function for it, so we just say we took the derivative. And we keep the denominator the same. Minus, now we keep the top the same. And we look at the derivative of the denominator, which is 2x, all of course divided by the denominator squared. Great, that's it. Do we need to clean this up? You can. I'm not going to, but you're welcome to. Just remember, if you make a mistake simplifying, it could throw off this answer, and it could throw off your final answer if you get it wrong. I think I'm just going to skip right to a prime of 2. A prime of 2 means we need to evaluate all this by replacing the x's with 2. 2 squared is 4. I think we can do that one. No reason to skip it through or take any more time than we have to. This is 2 right here. And then 2 times 2 is again 4. Very exciting. All divided by 4 squared. Can we stop here? Well, no, we can't stop here. The general rule to stop on a free response is if you take one of those like blue scientific calculators that you used in like Algebra 1 or geometry, the non-graphing calculator varieties, if you can take your answer here and type it into one of those scientific calculators, then you can stop. But my scientific calculator, I wouldn't be able to type in h prime of 2 or h of 2, right? It doesn't have that capability generally. So we need to keep working. Well, how do we keep working through? We just need to replace the parts that we can't type in. H prime of 2, we found that up above, it's 2/3. Okay? 4 minus, and then we have 3. H of 2, what is h of 2? I think we had that up here, right? H of 2, that's 4. That's exciting. So h of 2 is 4. And that's also a 4 divided by 16. And you can actually stop here. This is a valid answer on a free response. You're never asked to simplify, and oftentimes it's suggested you don't. However, should you simplify here? Yeah, it's your homework, it's practice, and the more we practice simplifying, the better we get at it. On the test, don't. You could make a silly mistake, but I'd suggest simplifying. So let's try it. 3's will cancel, right? That's cross-canceling. This becomes 8. And then 6 times 4, I think, becomes 24. So I'm looking at 8 minus 24 divided by 16. I'm looking at negative 16 divided by 16. Does that seem right? 16 and 8 is 24, which really looks like we had an answer of -1. What a nice answer. By the way, free responses do not always give you nice answers. I've gotten weird and wacky fractions and decimals before, even on non-calculator active questions. Well, how do you know this is a non-calculator active question? It's all about the question number. This is question number 6. There are 6 total free responses. So free response questions 1 and 2 are what's known as calculator active, meaning you not only are encouraged to use a graphing calculator, you actually have to use a graphing calculator to solve some or all of the pieces of those questions. However, FRQs 3 through 6 are non-calculator active, which of course means you are not allowed to use your calculator. You have to put it away after the second one, and then you can tackle the last 4. So this is question 6. We do not get a calculator, which is also why I suggest many times that you don't simplify. But either way, let's get to our last part. It is known that g of x is less than or equal to h of x. For 1 less than x, let's just 3. Let k be a function satisfying that k is between. So the outputs of k have to be between the outputs of g and h. All right, so what does that mean? Well, it means that if you plug a number in between 1 and 3, like 1.5 into all of these, and I'll erase this shortly, but if you were to plug in 1.5, this inequality has to hold true. Maybe g of x was like 12, well then k of x would either have to be equal to 12 or bigger than 12, and then h of x would either have to be equal to 12 or bigger than whatever k of x is, right? It's saying that the outputs have to follow that order. Is k continuous at 2? Well, this should jog forth some memories from our first topic, particularly when we discussed continuity of functions. That was, I think, between days 6 and 7. So let's go through it. To show a function is continuous, the first thing we need to show is that a point actually exists at 2. So what is k of 2? Well, k of 2 exists, and this one's a bit of a stretch here, but I think you'll be okay. K of 2 exists because g of 2 has to be less than or equal to k of 2, which has to be less than or equal to h of 2. And I think they told us up above that g and h are continuous, which means that all of their values are going to exist. You never have to pick up a pencil. So if this value is in between 2 continuous functions, then this value has to exist too. Right? Now, do we need to say any more about that? Maybe we could go a little bit further. We could say that g of x and h of x are continuous, that's probably not bad to say, because then it really, reaffirms that k of 2 has to be a value, and it's in between two other values, and that's fine. We know it exists. We don't have to find what it is. We just know it exists. However, we can also find what it is, because we know that g of 2 is equal to h of 2, which equals 4. They told us at the very beginning. So therefore, if k of 2 has to be between those two values or equal to those two values, then k of 2 must equal 4. Great. We're crushing it so far, guys. Let's continue on. The second thing we need to show is that the limit as k approaches 2, and I'll write this here, the limit as k approaches 2 of k of x exists. And there's two ways normally to deal with this with a limit. Number one is you use the one-sided limits, but we use that approach if k would be a piecewise function, and we don't even know that about k. They didn't tell us if it's piecewise or not. So what's the other way to prove or guarantee that a limit exists? Well, guarantee should jog forth that other theorem that we haven't used very much, the Squeeze Theorem. Now, this is where I felt like I was a bad teacher when this free response came out. I've always taught the Squeeze Theorem up to the point that I bet most other teachers taught it, which is I spent about 30 minutes on it when we introduced a few trig limits and then said, cool, you'll never see it again. Well, AP exam got the last laugh there. The kiddos definitely saw it again. Now, this problem was only like 2 points out of the total 54 for the free response. It was not a huge issue, but I bet probably none of my students got it, and I felt like an awful human. However, many students still passed that year. My pass rates didn't change. So now I'm just doing better at using the Squeeze Theorem, and you'll see it at least once a unit, if not more. What does the Squeeze Theorem tell us? Well, we first need to make sure we can use the Squeeze Theorem. Right? How do we use the Squeeze Theorem? Well, I always like to start with continuity. Right? Now, you don't need to, but I think it's probably good here to start any of your theorems with continuity. So I would do something like this, right? As g of x and h of x are continuous. Always good to start with continuous. We can't say k of x is continuous because that's what we're trying to prove, but let's use these other two functions because we'll need them shortly, right? As they're continuous, well then what do we know? Well, the Squeeze Theorem eventually, maybe I can even write the conclusion before I do this. The Squeeze Theorem is essentially going to say if g of x and h of x have the same limit and this is held up, meaning g is less than k less than h, then k of x also has that limit. So maybe I can even write that conclusion, right? G of x is continuous. I'm going to leave a gap here, and I think a whole line will probably be fine. So I'll just kind of leave this gap. We'll come back and fill it in. Then, that was the world's weirdest T. So we'll do something like this. Then, I'll need more space. Then the limit as x approaches 2 of g of x equals the limit as x approaches 2 of h of x means by the Squeeze Theorem that and actually I should say what this limit equals. We'll come back to that in just a second. That the limit as x approaches 2 of k of x equals that same value. Well, what do we need to show here? Well, I bet you're probably going to say, oh, we know the limit as x approaches 2 of g of x, and we know the limit as x approaches 2 of h of x. Do you? They told us the point exists, but how do we know as you get close to that point that you're also approaching 4? Well, I put it in yellow here, right? Continuity. These are continuous, which means, these are our 3 steps, right? It means that the point and the limit, if we were thinking g or h, are equal to the same spots. So as g of x and h of x are continuous, g of 2 equals the limit as x approaches 2 of g of x, and h of 2 equals the limit as x approaches 2 of h of x. Very important to state here, right? We need to explain to them how we actually know what those limits are. So as g of x and h of x are continuous, g of 2 and blah, 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 blah. Maybe instead of then, I should probably say, therefore, what are those values? Maybe we should even put that in here too, right? Those values were 4, weren't they? Oh, and therefore, 4 again. Therefore, 4 equals this means, by the squeeze theorem, that this also equals 4. So it's a bit of a mouthful there. I can probably be a little bit more elegant with how I phrased that, and it's because honestly I use the squeeze theorem the least out of any of these. I will get better at it, as will we all. But is that enough? Are we done? We showed that there's a point there. We showed that there's a limit there. Oh wait, I think there's one last part, and this is really our conclusion here, right? So as k of 2, we saw that up here, right? As k of 2 equals the limit as x approaches 2 of k of x, that's this piece right here, equals 4. This is a really easy statement to show that the point is in the same spot as the limit. As that blah, 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 then k of x is continuous at x equals 2. Remember those 3 steps of continuity. Is there a point there? Is the limit there, or basically does the limit exist? And last but not least, are the point and the limit in the same spot? Thank you for hanging out with me as we went through that quotient rule today. Of course, this free response only had one quotient rule, but it's good to get more free response practice. Your homework will have lots of quotient rule problems. Check my independent practice solutions. Please let me know if I make any mistakes, and I'm excited to see you back next time for day 19.